Hey guys, back for another lesson in chapter 7, continuing on. And again, I just hope over Thanksgiving break you guys can give me, an hour or two just working in chapter 7. Okay, here we go. What do you call a pig that does karate? Pork chop. And what happened when the pig pen broke? The pigs had to use a pencil. Oh, there you go. There's my silly jokes for today. Okay, I don't want to make this super long, but I want to just continue on in chapter 7. So here we go. Okay, so where we left off was with this problem right here. Okay, so a good problem to make sure that you guys can do. And again, what we're doing now is we're going over, we're learning about waves along with energy. And this is because waves exist in the form of, light exists in the form of waves, and some of the understanding of electrons and their energy levels outside the atom is done by studying waves, and so that's why we spent some time. So understanding that. We'll talk about it, maybe not today, but after Thanksgiving. Electrons kind of have wave-like behavior and particle-like behavior. But kind of interesting, the photoelectric effect, Einstein won a Nobel Prize in 1921 for this. He did not win it. And what all is written down here, you really don't need to know. You know, he did not win a Nobel Prize for E equals MC squared or some of the other great stuff he did. This is what he won the Nobel Prize for. You don't need to write this down or note this, but this is where showing how within matter, particles are acting like, or I should say protons, neutrons, electrons, specifically electrons are acting like particles. So if you look here, when light of short wavelength, so that would be more energetic, blue light is shown on alkali metals. Electrons are ejected from the metal surface. The number of electrons are proportional to the light intensity of the volume of light. So the more energy that these alkali metals are hit, the electrons propel faster. It makes sense. More energy coming in, then your particles are going to be moving faster. And it found the energy of the electrons is proportional to the wavelength of light, where the shorter the wavelength, the higher the energy of the ejected electrons. Really what's going on here, it's like the electrons and light are acting a little bit like pool balls. You hit the cue ball, which hits the 7 ball, which hits the 9 ball. That's what's going on here. So the diagram on the light, or on the right, blue light has more energy, a shorter wavelength. It is emitting the particles with more energy. The red light on the left is emitting light with less energy. And so, and you guys can look online, but Einstein reasoned that light was acting like a particle, which he called a photon. If the photon had sufficient energy in a collision with an electron, the photon would knock the electron out of its orbital. So this again, it's kind of significant. This is what Einstein won his Nobel Prize for, was this idea of, again, kind of almost like electrons and light acting like pool balls, acting like particles. And that led into this wave-particle duality of light. Einstein suggested particle-like properties of light could explain the photoelectric effect. So again, that's where matter is acting like particles. But diffraction patterns, which is, if you remember back, and I'll talk about this after Thanksgiving, but when we did the flame test and we did the light, we passed light through a gradient through a prism, and we were able to see the colors of we saw it like the colors of the rainbow. That's diffraction patterns. Okay. So Einstein reasoned that E equals MC squared, where E is energy, M is mass, C is the speed of light. And so, and you will not have to go through this derivation. You could, it's pretty simple. So if you rearrange mass is equal to E over C squared. And then if you remember back what we had earlier, E is equal to H, Planck's constant, times C, the speed of light over the wavelength. Well, then if we substitute in for energy, mc squared, and then rearrange, we can find the mass of a particle.
So are you out too?
I am. So Warren, they say we're supposed to be here tomorrow, so I'm just going to have everything right here.
Okay.
So if you can
for 7.
tell that. So
or 6, whatever.
Have a good Thanksgiving. Are you out?
Not yet.
Well, if you could just direct the sub, it'll be right here.
Okay. Perfect.
Thanks, man. Have a good Thanksgiving. Well, I think I'm okay, but
Yeah,
it
I think you're okay,
sucks.
but, yeah.
Right. Thanks, Warren. Hey, have a good Thanksgiving.
Yeah.
And so if I go back here and then rearrange this. So here are kind of the key equations, and this is something that you might want to write down on the formula sheet. This is already on the formula sheet. Number 1 is C is equal to the frequency times the wavelength. And of course, they use nu, the Greek letter nu, and lambda. And then we had E is equal to H, Planck's constant, times the frequency. And then we were using in the last lesson, E is equal to HC over the wavelength. Well, now we can also say that the wavelength is equal to H over MC. And this could be velocity. If we're talking about a particle, we're not talking about light, this could be velocity. And then we could rearrange this, and we could say that mass is equal to H times the wavelength over against C, or the velocity. Okay, so if we rearrange it, we would be like that. So these are the equations, and actually I am going to, if I'm going to have time today to get to a problem where we're going to do a simple calculation. Again, really more physics than it is chemistry. Okay, a little bit more. Okay, so again, what I put on the board behind me, and on your formula sheet, I would suggest maybe what I've got behind me, I don't know if you can see this, but right here, I would write that in. Okay, and if you notice the units and just how, again, the units cancel out, the speed of light, joules, kilograms, and how everything works. Okay, the duality of light. Light has both wave and particle-like properties. As a wave, again, it travels like a wave. That's what light does. As a stream of particles, again, like little baseballs or little pool balls. And then about 100 years ago, this chemist Louis de Broglie reasoned that if light would behave like a particle, then electrons, which until now were considered to be a particle, could have wave-like properties. So he is seeing, and this is what we're going to get to in the next lesson, but that electrons kind of are in between. They kind of have wave-like property and particle-like property. And this, by rearranging Einstein and Planck's constant, we get what I have behind me on the board, the equation for the wavelength is equal to H over MC. Okay, and I think that is a good place to go ahead and stop. So again, I would write down those equations, which I've got on the board right here behind me. I would write those back down on this sheet right here where it says atomic structure. It's really up to you if you want to do that or not, but I would suggest that. Tommy, have a good Thanksgiving. See ya. So, hey guys, have a good Thanksgiving, and I will see you soon. Bye.